and N for north, yes? So basically, it became this big navigation thing where if you wanted to know like your orientation and you wanted to know, well, which direction is which, you could just take one of these rocks, suspend it, allow it to freely swivel. One side would point north, you know, maybe this side over here was painted, you know, and then of course if you know that that's north, well, you know the opposite direction is going to be south, you know, and if that's north and that's south, east, west. So as soon as you kind of know where north is, you kind of like know all the directions. And apparently this like opened up like navigation in the seas like never before. I've seen descriptions where like sailors would have like a bucket of water. I think even like Christopher Columbus used this, yes? And here's your bucket of water. Yeah, there's the water, yes? And then inside the water, maybe it was a piece of wood, thank you, floating in the water. And then on top of the piece of wood, they would have one of these stones. And the picture I saw, they cut the stone so it looked like a little fish, you know, with like little fins over here. And basically the stone was kind of like attached to the wood there, yes? And since the stone was floating on a piece of wood, it was able to kind of like freely swivel. And basically, so the fish's head would always point in the northern direction. And the tails, you know, the fins would point in a southern direction. So again, this was a big deal because it kind of showed navigation. You could kind of see where north always was. Shortly after that, it was discovered that if you take one of these special rocks and you take another one, and let's say individually, isolated, all by themselves, each one would be pointing north, yes? But when you brought them near each other, they would stop pointing north, and then they would have this like big time effect on each other. And if this was the side that was etched out, you know, to say that it points north, then this guy here would swivel, woo, woo, you know, and line up so that its north, you know, would be pointing away, and its other side, the south side, would be pointing, yes? Even if you went in with like suspended a south and a south like this, you know, one of them would immediately kind of like swivel on the string and reposition itself so that this was the north and this was the south. So the side that always pointed north by itself was identified and called the north side or the North Pole. And the side that was on the other side over here was called the South Pole. And this is kind of important because in a moment it's going to get a little bit tricky and sometimes students get confused on this. But just get it straight from the beginning, you know. By definition, the side that naturally points north is called the North Pole. These rocks were called lodestones. And today we know that these rocks have a lot of iron in them. And they can actually be manufactured now. Whoopsie. a piece of steel which has a lot of iron in it, yes? If you take it, suspend it, I should say certain steels after they've been manipulated a certain way, have this same special property of swiveling naturally until one side naturally points north, and the side that naturally points north, it's etched out. That's called the North Pole, and the side that naturally points south, that's called the South Pole. And basically, we call this thing a bar magnet. And the whole device of a bar magnet being allowed to naturally swivel, that whole thing is just basically called a compass. A lot of times, a compass now could be like, you know, held in your hand. And basically, folks, instead of being suspended from a string, you have a bottom plate, and then there's a little pin, and then balanced on that pin, you have the bar magnet. And the bar magnet is free to swivel on that little grooved out little hole in the middle of the plate there. And it's so cool. On its own, one side naturally points north, and sometimes it's just like painted with red paint. Sometimes it's marked with an N. Sometimes it's marked with an arrow, like that. Sometimes students come to me, they say, I really don't know how to use a compass. There's really nothing to know. You just take it out, let the thing swivel around, and the side that has the N marked on it, or is an arrowhead, or has the little dab of red paint on it, or blue paint, or whatever it is, however that stops, you just know, oh, that's North Pole. People get messed up because the base thing has all the different directions labeled on it. Yes? What I say to them is ignore all those little labeling on the base directions and just look at the needle. Take it out, whichever way the needle points, that's north. Now, if you really want to get into it, what people do is once the needle stops and points north, they take that little base thing and they swivel it so that the N for north goes underneath the needle. Because then once the N is lined up, then you could look at all the markings on the base thing and you could see, oh, look, that way's north, oh, this way's south, and you could read that's east and that's west. But you don't really need to use all those markings on the base thing. You just really need to use the needle. And then as far as this business of having like opposite poles here attract, this reminds us of that electrostatic rule where you have opposite charges attract, like charges repel. But you know what? These aren't charges. These are sides of rocks. So you wouldn't want to say, oh, this is the rule, opposite charges attract. You have to use the right terminology here. You have to say opposite poles attract. So we have our first rule of magnetism. So the question is, why, when you have just one single free to swivel bar magnet, why does one side naturally point north? What's up with that? And the first hypothesis was actually incorrect. And you don't need to copy this down because it's, turned out to be incorrect. And again, people really weren't sure how the Earth was shaped, whether it was a sphere or something else. I'm just going to draw it here as a sphere. But, let's say you had your Earth right here. People thought that, this, of course, isn't drawn to scale. If you had your free-to-swivel bar magnet right here, that one side would naturally swivel. So this side would point north because they thought, oh, there must be like large mountains of lodestone up here that, attracted the North Pole. That's why even all by itself, one single free-to-suspend bar magnet would swivel, so one side pointed up north. Well, as we know, there aren't such mountains on top of the Earth. Okay. Scientist by the name of Gilbert he concluded that the Earth itself acts as if it's a bar magnet. The Earth itself acts like a big bar magnet. Now here's the thing, you know how the Earth is on a tilt, and here is the geographic North Pole? And down here is the geographic South Pole. The Earth acts like it's a big bar magnet, but the two bar magnets' ends aren't lined up with the two poles of the Earth. It's slightly off. It's more like this. Let me erase this. Gilbert said that the Earth acts like a big bar magnet, which has one end very close to the geographic North Pole and has the other end very close to the geographic South Pole. Now, here's the weird thing that a lot of times you don't really talk about, okay? But it just turns out, remember, people already decided before they even came up with these bar magnets and stuff that they were going to call one direction north, yes? And then there were these free-to-swivel bar magnets that one end naturally pointed north. So the side that pointed north, they called it the North Pole. And then they learned, oh, look, if you had two of these rock things, opposites attract. And then it was discovered, oh my God, the whole Earth acts like a big bar magnet. Well, one logical step after another, look how this ends up playing out. Again, of course, not drawn to scale, but if you have a bar magnet here that's tied and free to swivel, we know how bar magnets feel about other bar magnets. The side that naturally points up to the geographic North Pole, we know, we already called it the North Pole. It's the north side. It's the side that naturally seeks north. And this side over here that points, towards the geographic south was called the South Pole of the bar magnet. By definition, that's how it originally got its name. Yes? Well, if like poles repel and unlike poles attract, and the whole Earth acts like a big, gigantic bar magnet, don't shout it out. Think about it for a second. Which magnetic pole is going to, of the bar magnet that the Earth kind of acts like, is going to be up north where the Christians believe Santa Claus lives? The South Pole of this bar magnet. The Earth acts like a big bar magnet. However, up at the geographic North Pole, it's the South Pole of the Earth acting like a bar magnet. It's the South Pole of the Earth's bar magnet, as the Earth acting like a bar magnet. And this is because, this here and this here, opposites attract. This thing here, it's like showing that the Earth itself, the Earth really isn't shaped like that. But the Earth itself, the Earth is really shaped like this, okay? But it acts as if it's like a big bar magnet that's shaped like this. So this is the real shape of the Earth, but it behaves as if it's a big bar magnet just like this. That's why if you have another solo bar magnet over here, that's why one bar magnet all by itself out in the middle of the forest, you freely suspend it, why does it swivel and why does one side end up pointing up north? Right, because the Earth is like a big bar magnet whose south pole is at the top. Now, one thing that leads to a little bit of a problem. Okay, question, yeah.
Is it coincidence that the North and South Pole are located very close to the Earth's axis, the geographical?
Yeah, it's a good question, and more on that in a second, okay? Okay. It turns out that where these are located isn't a fixed situation, is not a fixed situation. It kind of changes. The Earth bar magnet kind of changes its rotation. As a matter of fact, what I'm about to say in a few more minutes after that, it not only does it kind of like change its orientation like this, okay, it actually has been known to actually reverse. Okay? So, but more on that to come. Okay? It's not lined up with the axis. That's what I was trying to say. Like, look, here's the bar magnet axis, yes, and here is the current axis of the of the Earth. It's not lined up. Now let me see if I could draw this three-dimensional diagram here. All right, this is not a pumpkin. This is just me showing the Earth here, yes? And let's say that, let me start over. shot.
Good try, I think.
Good try. All right. So, see if you can follow me on this, people. Here is the magnetic pole of the Earth. Here is the geographic North Pole. So the Earth, acting like a bar magnet, has one end right here, but yet the Earth's geographic North Pole is right there. Now, if you're standing like over here, and you have your free to swivel bar magnet, that turns out really not to be too much of a problem. Because basically, if this is north and this is south here, yes, and you're like out in the woods and this sucker here points north, it's going to point towards here, the south end of the bar magnet pole, which is really right on the direction to the geographic North Pole. So you're in kind of good shape if you were hanging out like over here. Yes? So in that case, hey, what a great thing. You know, the bar magnet points exactly towards this, which is right on the way to geographic North Pole, yes? But let's say, again, this is a three-dimensional picture here, yes? Let's say you're right here. Oh, I gotta re-switch this here. You know, and again, like, I'm on top of the Earth over here, three-dimensional picture here, yes? So here's my little bar magnet thing, yes? Well, where's it going to point? Well, it's going to line up with what? Hello. It's going to line up with what? This guy here, yes? That's where this thing's going to go. This thing is going to swivel until this north point swivels around and attracts to that south, yes? Now, is that true north, though? No. Look, true north is up to here. This is true north. Wah, wah, wah. Yes? But this thing's going to be pointing up here towards the South Pole. So sometimes the bar magnet doesn't even actually point true north. And this angle right in here is known as the angle of declination. And sometimes it's like 30, 40 degrees. Sometimes it's huge. The final thing I want to share with you, which Mike kind of brought out, okay, the orientation of the Earth acting like a bar magnet is not constant. Right now, this is the South Pole and this is the North Pole, but in the past, it's been reversed. This up here is the North Pole and this over here is the magnetic South Pole. By studying the rocks in the mid-Atlantic, what's that called, the ridge, yes? What happens is hot magma oozes out, yes? And as it oozes out, it's, it's liquid at first, it's this melted rock, which has a lot of iron in it, yes? And as the iron comes out, it cools, and the lodestone is lined up in a certain way, like this, yes? And the lodestone would be lined up right now with this North Pole up there and that south like this, yes? But what they have found out was, buried underneath that lodestone, there's other lodestone that's south-north. And buried underneath that, there's lodestone that's north-south. Which indicates that, all right, the magma can orientate its iron atoms any single way it wants when it's liquid. But then once it hardens, it's kind of like locked in place. So basically, the alternating setup of the way the rock is layered indicates that This now is a south, but years ago it was a north, and then years ago it was a south, and before that it was a north, and it's actually like switching every like 50,000 years.